All right. Good morning, everybody. Welcome back. I hope you got some rest during the spring break. So let's pick up where we left before taking a break. Okay. So let's start sharing my screen with you. All right. Starting with some important announcements for this coming week. We will have in class assignment this coming Friday on the 5th. So just be aware of that. And we have online homework for chapter 3, part 1. I changed the due date to Sunday. This is a very long homework, and it will take some time to get completed. So try to don't leave everything for the last minute, and then you have till Sunday 11:59 p.m. to complete it. Okay, so this was the last thing we talked about before we leave for a spring break. I talked with you about atomic molar mass. Remember that the atomic molar mass is simply the mass of 1 mole of atoms. And every time we are talking about mole is the same thing as replacing mole by 6.02 times 10 to the 23rd. The unit for atomic molar mass is grams per mole, or grams mole to the minus 1. And we can extract the atomic molar masses from the periodic table, okay? So it's always this number right here at the bottom of the box. And remember that this is the average atomic molar mass. And for example, the molar mass of potassium is 39.098 grams per mole. And that means 1 mole of potassium weighs 39.098 grams. And the amount of atoms in this mass is 6.02 times 10 to the 23rd. Okay, very good. Uh, so that was just a quick recap. So let's move on to new things. Okay, so today I would like to start talking about molecular mass. The elements are usually found combined with other elements. We saw that they need to achieve stability, therefore they will form compounds. And when elements combine to form compounds, there is no point in talking about individual atoms anymore. So now we need to talk about the compound as a whole thing. Therefore, the molecular mass of a molecule or a compound is simply the mass of 1 mole of molecules. And remember that mole can always be replaced by 6.02 times 10 to the 23rd molecules. And molecular mass, the unit for that is grams per mole, or if you want to write grams space mole to the minus 1. Okay, so when we are talking about molecular mass, we are going to factor all the atoms that are contributing in the compound. So imagine the molecule as a box, and inside this box, we will have all the atoms that contribute to the molecule. I would like to start an example here for the water, okay? So everybody knows that the formula of the water is H2O. And the goal here is to calculate the molecular mass for the water molecule. At this point, it doesn't matter how the atoms are connected. We are just interested in the molecular mass. Looking at the formula of the water, we can see here that there is an index 2 here. That means we have 2 mole of atoms of hydrogen, and there is no number here for oxygen. That means we have 1 mole of atoms of oxygen. If we go to the periodic table, we will extract the atomic molar mass for hydrogen, which is 1.01, and for oxygen, 16.0 grams per mole. So what's the molecular mass of the water? So again, we will factor all the contributions of all the atoms to form the molecule. Let me switch, sorry about that, to my other screen. Okay, great. So the molecular mass for the water, we are going to factor everybody that's contributing to the formation of the compound. So here we have 2 atoms of hydrogen, or better saying, 2 moles of atoms of hydrogen, and each mole of atoms of hydrogen has a atomic molar mass of 1.01. Okay. So this is the contribution from hydrogen. Plus, we have just 1 mole of atom of oxygen, and the atomic molar mass for oxygen in this case is 16. Okay. So this is the contribution from oxygen. Therefore, the molecular mass of water, we are going to get 18.0. Okay, attention here with the sig figs. So this is our limit, and the unit is grams per mole. Or you can also write grams mole to the -1. Okay, so the calculation of the molecular mass is pretty simple. Just add up everything that is part of the molecule or the compound, okay? Don't forget to factor the number of atoms that you have in the formula, and then just add up everything. And again, looking at the formula of the compound, you must be able to know how many atoms are there in the compound. Okay, so with that being said, let's do a practice here. And I would like to give you a couple minutes to try to solve uh, all the items in this example, and then we will do it together. All right, so let's see what you got here. Okay, so the example here is saying, consider a sample that has 2.5 grams of calcium fluoride. Item A, what is the formula of calcium fluoride? Okay, so everything starts with the formula. So that's what I was telling you some weeks ago. It's very tempting to look up uh, things. And if you don't understand things, that will slow you down in the future. And that's the point that will start slowing you down. So if I tell you calcium fluoride, you don't need to know right away the formula, but you need to have an idea how to get the formula of this compound. So this compound is formed by calcium, which belongs to the group number 2. Therefore, has 2 valence electrons, and to achieve stability is going to lose 2 electrons. Fluorine, on the other hand, belongs to the group 17. From the group 13 to the group 18, just subtract 10 and you have the number of valence electrons. We are going to get here 7 valence electrons. Therefore, the charge is going to be 1 minus to achieve stability. The combination of these two elements is going to produce CAF. Remember here to cross the charges because we have different numbers here. Therefore, we are going to get CaF2. Okay? And because we have group 2 with group 17, this compound is ionic. All right, so you have to be able to get the formula from the name of any of the classes of compounds that we have talked before. Okay, second part of the question. What is the molecular mass of calcium fluoride? All right, the molecular mass for calcium fluoride. Look at the composition of the compound. We have one atom, 1 mole of atoms of calcium and 2 moles of atoms of fluorine. So that's going to be 1 times the atomic molar mass of calcium. Going to the periodic table, we are going to extract 40.08. And this is the contribution from the calcium. And attention here, for each unit of calcium fluoride, we have 2 moles of atoms of fluorine. So we have to take this under consideration. And the atomic molar mass of fluorine is 19.00. Therefore, the molecular mass of calcium fluoride with 3 sig figs is 78.1 grams per mole, or you can write 78.1 grams mole to the minus 1. And that is our answer for item B. Okay, so in the calculation of the molecular mass, I will usually tell you the number of sig figs that I want, because if you go to the periodic table, you can find with like a lot of sig figs. So we will chop it up usually to 3 or 4 sig figs. Okay, so again, the molecular mass of a molecule or a compound tells us the mass of 1 mole of molecules. In this case, for the calcium fluoride, 78.1 grams, that corresponds to 1 mole of calcium fluoride. And that is the idea that I'm going to use to solve item C. Okay, so again, you can always write this as a conversion factor. 78.1 grams of calcium fluoride corresponds to 1 mole of, of calcium fluoride. Okay, so this is the molecular mass, 78.1, and that corresponds exactly to 1 mole of calcium fluoride. So look at that as a simple conversion factor, and then we can use a simple proportion to solve the problem. Okay, so the question is asking us how many moles of calcium fluoride are in 2.5 grams. So let's organize here the first column. I'm going to place everything that's in grams, starting with what I know, 78.1 grams. And in the second column, I'm going to place everything that is in mole. And I know that this mass corresponds to 1 mole. Okay, so remember that the first line always comes from the conversion factor. is always something that we know for sure. And we will divide. The question is asking us for 2.5 grams, and I want to know the number of mole. To solve that, simple cross multiplication, 78.1 grams times x equals to 2.5 grams times 1 mole. We need to isolate x, therefore 78.1 is going to move to the other side, doing the opposite operation. 2.5 grams times 1 mole divided by 78.1 grams. Grams you cut with grams. And according to my numbers here, this division is going to yield 0.032, and the unit that's left here is mole. Or you can represent that in a more elegant way using scientific notation, 3.2 times 10 to the minus 2 mole. And this is the final answer, just put inside the box. And that is going to give you the final answer. Okay, so this answer tells us that 2.5 grams of the compound calcium fluoride corresponds to 0.032 moles of calcium fluoride. Okay, so I'm running out of space here at the bottom, so sorry about that. I'm going to move D all the way up here. Then I can have a little bit more of space. Okay, so the second part of this question is a little trickier. How many atoms of fluorine are in a sample containing 2.5 grams of calcium fluoride? So let's start with the formula of the compound. So we have here CaF2. Let's consider that we have 1 mole of molecules. This compound is composed by 1 mole of atoms of calcium. Okay, so these numbers come from the index right here, and 2 mole of atoms of fluorine. However, the question is not asking me how many moles of fluorine are in the sample. Instead, is asking how many atoms of fluorine are in the sample. Very simple here, guys. We are going to replace mole in both cases by 6.02 times 10 to the 23rd. Okay, so that means in 1 mole of calcium fluoride, we have 1 times 6.02 times 10 to the 23rd atoms of calcium, and 2 times 6.02 times 10 to the 23rd atoms of fluorine. And that is the strategy that I'm going to use to solve this problem. let's try to build our conversion factor. 1 mole of calcium fluoride has, we are looking at fluorine, so let's look at this line, 2.602 times 10 to the 23rd atoms.
Hi, I'm really sorry. I was curious, is this supposed to be showing on the screen?
You cannot see?
Maybe it's just my screen. I'm having bad internet, so it could just be me. Is anyone else having the same issue?
No, I can see it.
Okay, I'm gonna restart my computer.
Yes, try to log out and log back in.
Got it. Sorry about interrupting.
That's fine. No, that's a bummer. Okay, so 1 mole of calcium fluoride has 2 times 6.02 times 10 to the 23rd atoms of fluorine. Okay, so this is going to be our conversion factor, and I extracted this information from the formula. Okay, so always look at the subscripts here, because that will tell you the number of atoms in the formula. And remember, mole can always be replaced by 6.02 times 10 to the 23rd. And here we need to know the amount of atoms of fluorine, and that's why I replaced mole by 6.02 times 10 to the 23rd atoms of fluorine. Okay, so with that, we can organize our proportion. So my first column here is going to be mole of calcium fluoride. So we have here 1 mole. And the second column is going to be atoms of fluorine. And we know that in 1 mole of calcium fluoride, we have 6.02 times 10 to the 23rd atoms of fluorine. Actually, you don't need to write everything here because we know that. And then let's divide by the information that we have. So 2.5 grams of calcium fluoride from item C, we know that this is 3.2 times 10 to the minus 2 mole. Okay, so this came from item C. And the question here is asking us how many atoms of fluorine are in the sample. All right, so to solve the proportion cross multiplication, we are going to end up with 1 mole times x equals to 3.2 times 10 to the minus 2 mole times, running out of space here, 2 times 6.02 times 10 to the 23rd atoms. Okay, so if you got all the way to this point, it would be a shame if you missed the final calculation. So attention here, because we have a multiplication of powers. Every time you multiply powers, you keep the base and add up the exponents. Attention here, because you have 10 to the minus 2 times 10 to the 23rd. So it's going to be minus 2 plus 23rd. And according to my numbers here, this is going to be equal to 39 times 10 to the 21. Oops. to the 21 atoms of fluorine. I'm sorry, this got really squeezed here. Or if you want to represent in a more adequate scientific notation, that's going to be 3.9 times 10 to the 22 atoms of fluorine. Okay, so stoichiometry is a little bit trickier and it will require a lot of practice, okay? So let's keep working on that. Okay, so let me move back to the PowerPoint. Okay, so now let's get back to chemical equations. Remember that a chemical reaction is basically a rearrangement of atoms, and atoms cannot be created or destroyed. In a chemical equation, on the left side, we always have the reagents, or also called reactants, and on the right side, we have always the products. The numbers in red represent the stoichiometric coefficient, and it's going to give us the ratio between the two reagents in this case and how much product is formed. Okay, always pay attention to the stoichiometric coefficients. And in blue, what we have is always the physical state of each component. If you know the physical state, you can put in the equation. If you don't know, then leave without it. The stoichiometric coefficients in the chemical reaction will tell us the proportion between reagents and how much product is formed. Thus, knowing a chemical reaction for a given process allows one to predict the amount of product or products formed or reagent needed. Okay, so look at the chemical reaction as a simple cooking recipe. So this is what you need to start with, and this is your end product. For example, if you combine 1 mole of atoms of A with 2 moles of atoms of B, you are going to produce 1 mole of AB2 molecules. Okay, the stoichiometric coefficient, we always give you the proportions. And again, just look this as a simple recipe. Okay, don't panic. When you panic, you do stupid things. Just be sure of what you are doing here. And once you know the ratio or the proportions, then you can extrapolate that for any amount. For example, here, if I have 2 moles of atoms of A, from 1 to 2, I'm doubling, so I have to double everything. So everything in the reaction is a proportion. If you double or triple one amount, all the other amounts have to do the same, to keep the proportion. Okay, in some cases, I will provide you the stoichiometric coefficients, but in other cases, you will have to adjust the stoichiometric coefficient. Remember that a chemical reaction is always a rearrangement of atoms, and atoms cannot be created or destroyed. Therefore, the number of atoms of a given element that shows up before the reaction has to be the same after the reaction. So let's take here as an example the formation of the water molecule. Very simple reaction, a combination of hydrogen gas with oxygen gas, and that produces water in the liquid state. Let's represent hydrogen by black colored spheres or circles better here, and oxygen the blue ones. If we start with 1 molecule of hydrogen and 1 molecule of oxygen and end up with 1 molecule of water, 2 hydrogens, they show up in the products. However, we have 2 atoms of oxygen in the reagents and just 1 atom of oxygen in the product. So we are disappearing or destroying 1 atom of oxygen. So this cannot happen. And that's why we are going to balance reactions to make sure the amount of atoms before is the same of the amount of atoms after the reaction. Balancing a chemical reaction is simply adding coefficients here in order to have a balance in the number of atoms. So in this case, it's quite simple. If we balance this reaction using 2, 1, and 2, now we started with 4 atoms of hydrogen, and at the end, we still have 4. 1 times 2, 2 atoms of oxygen, and 2 times 1, 2 atoms of oxygen at the end. Okay, look at the figure. 4 black circles, 4 black circles at the end, 2 blue ones, and 2 blue circles at the end. Therefore, this reaction is now balanced. And again, read the reaction as it was a recipe. On the left side are the ingredients that you need to start cooking. And on the right side is your final product. This reaction tells us that we need 2 molecules of H2 reacting with 1 molecule of O2, and that will produce 2 molecules of water. If you change one of the reagents, the other one has to change as well to respect the proportion. And that's how we can predict the amount of reagent needed or the amount of product produced. Okay, how do you balance a reaction? For now, we are going to use the trial and error method. So we will guess numbers and see if we can match up the amount of atoms before and after. In the chapter number 4, I will show you a method that has more of a mathematical background. Okay, so let me show you a couple of examples here that we still have time, and then I will leave the other 2 for you to try by yourself. So let me just quickly change to my other screen. Okay, so I will start with the first one. Let me rewrite here. So we have here NaBH4 in the solid state, reacting with water in the liquid state. So those are my ingredients to cook. And the result of my cooking is NaBO2. AQ means aqueous, in other words, dissolved in water. And I'm going to also produce hydrogen gas, okay, H2 gas. Looking at the reaction, we can see here that we have just 1 atom of oxygen in the reagents and 2 atoms of oxygen in the products. So that means the reaction to start with is unbalanced. So my strategy here is to start balancing the number of oxygens. Why am I choosing oxygen? Because there is just 1 compound that has oxygens in the product and in the reagents, okay? So when that happens, that's a good strategy, that's a good starting point for balancing the equation. We have here 2 oxygens, okay? So the index here determines the amount of oxygens and just 1 here. Therefore, I'm going to multiply the water by 2. So that's our first stoichiometric coefficient. So this number in front of the compound is always going to multiply the indexes. Now, let's count the number of hydrogens before the arrow. Okay, so now we have to factor everybody that has hydrogen before the arrow. So let's start with the first compound. We have 4 hydrogens. The second compound, we have 2 times 2, attention here, we have to multiply the stoichiometric coefficient by the index. Therefore, we have 4 hydrogens, which gives us a total of 8 hydrogens before the reaction. Now let's move on to the products and let's see where are the hydrogens. And we got very lucky here. There is only one compound that has hydrogen in the products. Look, is the second product here. If we have 8 atoms of hydrogen before, we have to have 8 atoms after, which means the stoichiometric coefficient has to be 4. Okay, so remember that the stoichiometric coefficient will multiply the index 4 times 2, 8 hydrogens. And now we check everything else to make sure we don't need to balance anything else. Sodium, we have 1 before and 1 after, so that's good. Boron, we have 1 before and 1 after, that's good as well. If you leave the reaction like that, I'm more than happy. Or you can add the number 1 before NaBH4 and before NaBO2. If there is no 1 there, I understand, I know that it has to be 1. Okay, so leave but 1 or leave without 1, it doesn't matter. Okay, there is a little bit of time to start the second example. So we have here sodium chloride reacting with sulfur trioxide. Oops. And we also have water in the reaction. And we are going to produce sodium sulfate, AQ. Again, AQ means aqueous or dissolved in water, plus hydrochloric acid also dissolved in water. Okay, so again, try to identify the element that is unbalanced. And if you can find just one reagent and one product with this unbalanced element, that's a great point to start. Here, I'm going to start with hydrogen, but you also can start with sodium. We have 2 hydrogens before the reaction and just 1 after the reaction. That's a red flag. That means we have to balance this reaction. 2 before and 1 after, just need to multiply by 2. Remember that the stoichiometric coefficient will multiply the indexes. Now, because we added the number 2 here, we have 2 atoms of chlorine. Move to the reagent side. The only compound that has chlorine is sodium chloride. If we have 2 after, we need to have 2 before the reaction. So just multiply by 2. And see that now the sodium is also balanced because we have 2 atoms of sodium and 2 atoms of sodium afterwards. That's great. Now let's double check the sulfur and the oxygen to make sure we don't need to do any extra balance. 1 atom of sulfur after the reaction, one atom before. Sulfur is good. Now let's count the number of oxygens. 3 plus 1, 4. And we have 4 on the other side. So let's just add 1 for everybody else. And the reaction now is happy. Now it's balanced out. And now we know all the proportions. So unfortunately, we don't have time for C and D. So I'm going to give you the answer here. For C, we have 4, 18, 1, and 8. And for D, that's going to be 3, 2, 1, and 6. Okay, so balancing is trial and error. Start with a number, and then we will adjust the numbers accordingly. Okay, so that's right on the mark for today. So I will stop here, and I will see you tomorrow, and then we will return with lecture on Wednesday. Okay, so I hope you have a good week. If you are on campus, I'm all the time in my office here. If you want to stop by, you are more than welcome. Okay, have a good week.
Thanks, Professor.
Thank you.
Thank you.
Bye-bye.
Professor, I've got a question for you real fast, if you have a second.
Yes.
It's just about significant figures. You were saying that you were always going to ask us or tell us how many significant figures you want in our answers.
Usually,
I guess
yes.
it's just kind of a curiosity question. What if there's never, I want 3 significant figures on your answer. Is there kind of a general standard for how many you should round to if there's none given?
Oh, I see what you mean.
Not that it'll ever come up, but I'm just kind of curious.
Yeah. If I don't tell you anything, so what I usually will do, let me share my screen with you. See here, for example, for this example here for the water.
Mm-hmm.
So I will give you the atomic molar mass for each element. And that will be your clue for the number of sig figs.
Okay.
Okay?
Okay, got it. Thank you.
Yes. Bye-bye.
All right, we'll have a great rest of the day, Professor.
You too.